Good morning. In today's training session, we will discuss regarding the general principle of radiographic inspection, type of radiation source that are in generally used into the industrial application, their character. So, in industrial radiography, basically we are using a ionizing radiation, which is emitting the electromagnetic radiation, and those radiation has a very high penetration ability due to its high kinetic energy. When the radiation is passing throughout the material, then it will be attenuated with respect to their density. That means the material which containing different type of dense material, dense part, that will be attenuated according to that. And attenuation of radiation, that means energy loss, is linearly proportional with the density of the material. So, if the different dense material is there associated into your inspection part, definitely the amount of radiation that will be reaching to the photographic film. Here, the photographic film we are using to record the transmission ratio of radiation, and the degree of radiation that will reaching to the film, that will be different, and that amount of radiation which is reaching to the film, that will be proportional to the degree of blackening into the film. So the degree of blackening into the film, that is associated with the radiographic film. So after the radiation exposure, and when the film is generally chemically processed to conform into the permanent image, we are getting the black and white image. It's a grayscale image, and the black and white image formation is due to the amount of radiation that is reaching to the radiation film in a different way. When we are using the talking about the electromagnetic spectrum, all the radiation sources which is emitting the gamma radiations or the X radiations, that all are under the category of electromagnetic spectrum, and all the electromagnetic spectrum has some unique energy. The energy is X-ray and gamma ray. These two type of electromagnetic radiation we are using for our industrial radiographic purposes. All the electromagnetic radiations, either it is the X radiations or gamma radiations, have the same type of characterizations, only the productions phenomenon, or how the X-ray and how the gamma ray is produced, that is different. Both have the frequency, wavelength, and velocity, and all are containing some energy packets, which is known as the photons. The main thing of the electromagnetic radiations, that they are not detected by the human sense, and they are traveling into the velocity of light. So that's why it is a very high kinetic energy, and its penetration power is very high. All the electromagnetic radiations cannot be changed by the electrical or the magnetic field. They can be transmitted, reflected, or can produce some kind of diffracted signals from the grain boundaries when the radiation is transmitted from one material to another material. When it will transmitted from one material to another material, definitely its loss is energy, and due to the loss of energy, there will be some hazards in case of human body or the living tissue is concerned. So in generally, by principle, we can say in the radiographic testing, the basic principle of radiographic testing is the differential absorption, where the different parts of the object will be absorbed with the different type of different amount of radiation, depending upon the thickness of the material, density, and atomic number. And when the image will be formed into the photographic film, it will be the grayscale image, that is it's a black and white indication. Before going to know elaborately regarding the radiographic technique, just we will remember regarding the atomic structure. We know that atom is the teeniest particle of any atom or any element which cannot be divisible. So when we are talking about the structures of atom, we know that the atom has two parts. One is known as nucleus, and the surroundings, that's some orbit, and the electrons are the particle which will be revolved into the orbit. And the center of the atom, that is known as the nucleus, is consist of two particles, proton and neutron. Proton and neutron, all these three particles associated into the atom. Proton has the positive charges, but its mass is negligible. Neutron, it's a unique mass, but it has chargeless element. And the electron, which is revolving towards the orbit from the center of the towards the center with the nucleus, that's a very very negligible mass, but it's a negative charge. So in general conditions, atoms are stable. The cause is the number of protons present into the nucleus is equal to the number of electron that is into the outermost cell. The number of protons or the number of electrons, that is known as the atomic number of any element. And when we are considering the summations of proton or neutron into the nucleus, that will be known as the mass number. So due to the higher number of neutrons into the nucleus and due to the heavier momentum, some element has a very very unstable nucleus, and those unstable nucleus will be split to the conservations of their momentum. And when the nucleus splitting will be there, some particles will be emanated from the nucleus. It's maybe alpha, beta, or neutron itself. If the alpha particle is emission due to the splitting of nucleus, then that particular type of element will be known as the alpha emitter. When the alpha is emitted from the nucleus by the nuclear fission or nuclear splitting, then the alpha has a atomic structure like that of helium. So when the alpha particle will be liberated from the nucleus, the atomic number will be reduced by 2 and the mass number will be reduced by 4 also. The material like the radium-226, uranium-238, and polonium-239 all are the radioactive element, and all these radioactive element will be creating the alpha emission. Similar way, some beta particle is emitted from the nuclear fission, and where the nucleus with the unstable ratio of neutron to protons is decaying throughout the emission of high speed electron called the beta particle, and this results in the neat change of 1 unit of atomic number. And the gamma rays, that's nothing, it's the energy packet generally we are getting from radioactive element which has very, very unstable nucleus due to the higher number of neutrons in their cell. And the nucleus, which is an excited state, may emit one or more photons, that's the packet of electromagnetic radiation, and discretes the energy. So the emission of gamma rays does not alter the number of protons or neutrons in the nucleus, but instead has the effect of moving the nucleus from the higher to the lower energy state, and it will be unstable to stable. So gamma ray emission frequently follows the beta decay, alpha decay, and other type of nuclear decay process. When we are talking about the industrial radiographic sources, so there are two type of radiation source we are using. You know very well, that is gamma radiation sources and X radiation sources. Gamma radiation sources are nothing. It's the radioactive element which are artificially produced into the neutron bombardment process in the nuclear reactor. Iridium-192, cobalt-60, selenium-75, cesium-137, and thulium-170. These are the type of radiation source which we are basically using into the industrial radiographic purposes. Mostly usable radiation sources which are using as radioisotopes, that is iridium-192, cobalt-60, and selenium-75. All these radiation sources, iridium-192, cobalt-60, and selenium-75, are produced in a nuclear reactor by the process of neutron bombardment. And when the iridium, that is naturally occurring element, is occurring into the state of iridium-191, when neutron is bombarded with this atomic structure, then it will be converted to iridium 192. And when it will be converted to the iridium 192 by the absorbing of neutrons, and it will produce the beta decay. And during this beta decay, it will be converted to the platinum, and gamma rays will be emitted from the nuclear fission. In the same way, cobalt, which is naturally occurring element, is cobalt 59, bombarded with neutron, converted to cobalt 60. It's also a beta emitter. After the beta emission, it will be converted to nickel, and when the beta emissions will be there, along with that we are getting the gamma radiation spontaneously. Selenium, that is 74 in the natural state, that is bombarded with neutron to convert it to selenium 75. It's also a beta emitter, and it will be after the beta decay converted to bromine, and we are getting the gamma radiation. When we are using these isotopes, then basic things of the definitions of isotopes is when two element has the same atomic number but different mass number, then it will be known as a isotope. Iridium 192 and iridium 192, 191, both have the atomic number of 77, but both have a different mass number. That's why it will be known as a isotope. Iridium 192 is in a radioactive form. That's why iridium 192 will be known as a what we can say, it is a radioisotope. So when all these radioisotopes 192, cobalt or the selenium is activated into the nuclear reactor, they have a specific dimensions, and when the specific dimensions in a small plates in a like that of circular discs, all are bombarded, and a different amount of activity is produced into the nuclear reactors. All these are put it into a capsule, and then it is welded, and all kind of mechanical testing activities has been done, and further it will attached with a pigtail, and that pigtail is normally inserted into a shielding container that is known as the radiographic camera or radiographic devices. So in the radiographic devices, this radioactive element, which is in the form of capsule and pigtail formation, that are stored when we are not using it. For that means for the safe storage and to restrict the radiation from the unwanted or unauthorized radiation hazards, it is kept into the safe manner into a devices that is known as radiographic camera. So when we are need to carry out the radiography into the sites or into the requirement, then we are connected this pigtail with a driving unit, and that driving unit end part is connected with the end part of the pigtail, and some kind of locking arrangement is there when the lock all are opened, and it is connected with the front extension guide tube, and when we are revolving this one into the clockwise direction, then the reserve spring will be pushed the radioactive isotopes to the out of the camera, and after the certain exposure time it will be returned back to its original position. When we are using the radioactive element, that is as a radiation source, iridium, cobalt or selenium, we need to be known some of their character. First thing, we need to know the first character, that means the identifications of radioisotopes or radiation sources determined by its activity, and the strength of the radiation source is denoted by its activity, and that unit of the activity is Curie. That is the older unit, and the present unit as per the SI unit, it is the becquerel, and by definition the Curie is 3.7 into 10 to the power 10 disintegration per second. When we are getting the relationship between the becquerel and Curie, one becquerel equal to 3.7 10 to the power 10 disintegration per second, or Curie. So one Curie equal to 37 gigabecquerel. When we are considering the one Curie source of each and individual radioactive element, it has some universal constant that is known as RHM value. That means the radiation intensity getting from the one Curie source from the 1 meter for a particular type of radioisotope is universally constant, and the intensity that is measured with respect to the radiations, that is in the Ranjan. So Ranjan is the amount of radiation in a particular area which can produce the one electrostatic unit of charge at STP. That amount of energy is normally considered the one Ranjan. The thing is, when we are talking about the iridium, selenium, or cobalt, both all have the different RHM values. So the values of RHM indicate that the amount of radiation intensity at the 1 meter distance from the 1 Curie source. So iridium 192 has a RHM value of 0.5 R, which is equivalent to 500 milliranjan. Cobalt 60 is a 1.3 R, which is equivalent to 1300 milliranjan. Selenium 75 that is equivalent to 200 milliranjan. The energy of individual radiation isotopes, that is also different. During the disintegration process, it's the average energies we are getting from a particular radioisotope. In case of iridium 192, the average energy of the gamma radiation sources is 440 kiloelectron volt, which can able to penetrate up to the 60 thickness of steel. In case of cobalt, it is a 1330 kiloelectron volt, and it can able to penetrate to 138 of steel, equivalent to the steel thickness. And selenium, that has a very soft radiation, it's an average energy of 200 kiloelectron volt, and it can able to penetrate up to 30 of thickness. When we are talking about the radiation isotopes, all have some decay constant, and the decay rate is denoted by its half value. Each and individual radioisotope has a half values, and the half value means the amount of time, a time duration in which the activity of the radiation source will be reduced to half. If the activity will be reduced to half, definitely the amount of radiation intensity will be reduced accordingly. Iridium 192 has the 74 days half-life, cobalt 60 has a 5.3 years half-life, and selenium 75 has a 128 days half-life. When the radiation is transmitted from the point of source to the forward directions, the intensity of radiations will be gradually decreases, and the degree of radiation will be decreases with respect to the square of its distance, and it is normally denoted by the help of Newton inverse square law. According to Newton inverse square law, the radiation intensity in a particular point is inversely proportional to the square of the distance from its originating source. So that means when we are maintaining the distance, we are going to be increases the distance from the radiation source. Radiation intensity will be reduced to the square according to the increase or decrease of the distance. When the radiation is passing throughout the material, definitely it will be lost its energy or lost its intensity, and this loss is depends upon the thickness of the material and the density of the material, and it's a equation I equal to I0 into e to the power minus mu x that we are normally using to identify the transmission ratio of the radiation when it will passing throughout the values of the x thickness material, which has the attenuation values of mu. Mu means the attenuation. This is known as linear attenuation coefficient value, and it is nothing, it is the energy loss per centimeter. When the radiation is passing throughout the material, definitely due to the attenuation, its intensity and energy will be reduced, and the thickness in which the radiation intensity will be reduced to half of its original, that is known as the half value thickness. And when the radiation intensity or the energy will be reduced to the 1/10 of its original, it will have a 10th value thickness. For an individual radioisotope and for the individual type of uh, material have a different type of HVT's value. The material which has a lower HVT's value can be considered as a good shielding material in case of the protection of radiation. For example, in case of iridium 192, concrete has a HVT value of 44.5 still it is 12.7 For lead it is 4.8 tungsten it's a 3.3 and the uranium, depleted uranium, it's a 2.8 So depleted uranium is much more shielded shielding efficiency is much more high compared to tungsten, then lead, then steel, then and concrete. So when we are talking about for the radiation protection, the preferable material will be the depleted uranium, then tungsten, then lead, and then steel, and finally concrete. When the radiation is passing throughout the material, it will lose its energy in the form of some kind of interaction process, and one of the first interaction process is the ionization. That means when the radiation is passing throughout the material, it can able to produce some positive and negative ions into the intermediate layers from where it will be transmitted. And the source of radiations is due to the different type of attenuation is there. That means there are different type of mechanism by which the radiation will be attenuated with the matter. So interaction of radiation with the matter can be occurred into the different way, like that a photoelectric effect, Compton scattering, and pair production. Photoelectric effect is in generally occurred into the absorbing material, yeah, absorber material, when the gamma or X radiation energy has a moderate energy. That means up to 400, 500 kiloelectron volt. In that much amount of energy can able to expel the electron from the outermost cell. And when the electron from the outermost cell of the transmitted material has been liberated, this process is known as photoelectric effect, and the electron which will be emitted, that is known as the photoelectron. If the energy of the gamma radiation is little bit higher, that is more than 500 kiloelectron volt, but up to 1.02 MeV, then it will be able to be interacted throughout the nucleus, but due to the internal scattering, it will lose its energy, and the remaining energy will be transferred to the another atom for the productions of photoelectric effect, and the photoelectron will be produced. So Compton scattering means it's the process by which the radiation can be penetrated by the phenomena of the scattering of the radiation throughout the internal orbit, and the remaining energy will be transmitted for the expel of the electron from their outermost cell. And third kind of interaction process, that is known as the pair production. And in the pair productions occur only when the X-rays and gamma rays have very high energy. That means the energy is more than 1.02 MeV. By that effect, the gamma rays is transformed to the matter into the form of pair of negatively and positively charged electron, that is known as the positron and neutron pairs, and that's why it is known as the pair productions. And finally, there is a radiation source which is known as X-ray. In general, in medical, we are using the X-rays, that is a very soft in energies. But in our industrial applications, we are using the X-ray machine with a reasonably very high energy. It may be vary from the 250 kiloelectron volt to up to 25 mega electron volt, depending upon the penetrated thickness. But the basic mechanisms of the X-ray production process is, in X-ray machine, there is a tungsten filament, and that tungsten filament is heated up due to the applications of current. Tungsten is a high atomic number material. Due to the high atomic number, it has a number of orbits will be more, and the number of electrons in their outermost cell will be maximum. And the outermost electron is loosely bound with the nucleus, so that when the current will be passing throughout the filament, it will be converted to the heat, and that heat energy will produce the expel of electron from their outermost cell, which is known as thermionic emission. And when the thermionic emissions will be there, electron cloud will be generated. Thus, electron is a negatively charged particle. So if we are using a target of positive terminal, and the potential difference between the cathode and anode, positive and negative terminal, is created, and due to this potential difference, this electron cloud will be accelerated and attracted toward the target. Here we are using the another target that is also made of tungsten, and when this electron is bombarded into the target tungsten material, it can able to expel the electron from their inner orbit, and when the one inner orbit electron will be ejected from that target element, then another electron from their upper shell will be jumped, and the energy difference between the two shells in their target material will become in the form of X-ray, and that X-ray we are using for the industrial application purposes. So when we are using the X-ray technologies, definitely X-ray machine has the uniform wavelength, and the energy is very the spectrum of the energy is not in a very concrete way. So that's why the quality of the radiograph which is produced by the X-ray will be very high. In case of X-ray machines, for the controlling of the X-ray machines, there are some parts of there. One is known as the tube, that is the measured by the tube current. Higher the voltage, that is known as the generator, to measured by the kV, and the control unit is there. And due to the thermionic emissions and as well as the bombardment into the target, most of the energy is converted to the heat. Due to the high rate of heat production, X-ray machine is normally very heated up. To come down into the cooling state, a cooling mechanism is there such that it will be immediately cooled, and all type of internal structures of the X-ray will be not affected. In here, the intensity of the gamma ray, which is proportional to our exposure time, that is depends upon the tube current, and that is denoted by milliampere, and the penetration capability of the X-ray, that is depends upon the kV value, and that kV is purely depend upon the potential difference between the positive and negative terminal, that is cathode or anode. So when we are talking about the X-ray machine, there are two parameters. One is the kV and second is the MA. MA is directly controlling the intensity of X radiation, which is proportional to our exposure time, and the kV value, that is directly proportional with the penetration's power, because the penetration is clearly depends upon whatever the energy is there. So that's all about the type of radiation source we are using in the industrial application. So gamma radiation source in the form of radioisotope like iridium 192, cobalt 60, and selenium 75, and in some cases the X-ray machine is using particularly for the non-ferrous material, or where the thickness of the steel equivalent to the steel thickness is very less. So in case of lower thickness or in case of higher thickness material, and particularly for the non-ferrous material, X-ray we are using to getting the proper level of quality. To get the proper level of quality into the radiographic exposure or radiographic technique, we are depending upon the X-ray in case of lower and higher thickness. But from the 4 thickness to up to 138 we are preferring the gamma radiation sources, because all the gamma radiographic cameras are enclosed into the radiographic equipment which is portable in nature. But in case of X-rays, definitely it is a very bulky appearances, and the weight of the X-ray machine is very high. So particularly into the construction or where the job is not movable and the radiography need to be taken into the constructions or inside, we are purely depends upon the gamma radiation source. Thank you for the today's class. In your second class, we will be discuss regarding the radiographic film system and the image formation and film post processing details into our next video. Thank you for listening.